All right, let's jump right into this. On July 27th, Moonshot AI is officially dropping Kimi K3. And I've got to say, it is fundamentally shifting the entire landscape of artificial intelligence. Basically, Moonshot is taking the entirety of their highly anticipated frontier-class model and just moving it straight into the public domain.
The sheer scale of this release is honestly staggering. We are talking about 2.8 trillion parameters. To put that into perspective for a second, this parameter count officially crowns Kimi K3 as the absolute largest open-weight model ever shipped to date. And on the surface, this is a developer's absolute dream. It effectively offers a frontier-class intelligence system, one that rivals the very best proprietary models on the market right now to literally any developer with an internet connection. The weights are out there, the intelligence is just free to download. Okay, let's dive into this, because this is exactly where the massive hype collides violently with physical reality. Sure, you can click download, but can you actually run it? For the vast majority of the industry, the answer is a hard, resounding no. In fact, running this downloaded model is basically a physical impossibility for most independent developers and your standard server setups.
And here is the exact reason why. 1.4 terabytes. This is the massive, completely unavoidable barrier to entry. And just to be absolutely clear here, we're not talking about 1.4 terabytes of standard hard drive space. No, this is 1.4 terabytes of incredibly fast, hyper-expensive GPU memory. You see, a model's weights have to be held securely in this active VRAM because the processor needs immediate, high-bandwidth access to them just to process a single token of a prompt. If you can't load that entire 2.8 trillion parameter capacity into fast memory all at once, the AI simply cannot function. Period.
Now you might naturally be thinking, hey, can't we just compress the thing? Well, that's the kicker. 1.4 terabytes actually is the highly compressed absolute best case scenario. Moonshot specifically trained this model to be quantization aware, so they're shipping the weights in MXFP4, which is a specialized 4-bit format. If you do the math, multiply 2.8 trillion parameters by 4 bits, you get exactly 1.4 terabytes. Without this intense level of compression, say you tried to run Kimi 3 in standard 16-bit precision, you would need an impossible 5.6 terabytes of fast memory. So yeah, 1.4 terabytes is literally as small as this giant gets.
So to truly understand why this model requires so much static memory, we have to take a look under the hood at its architecture. Kimi K3 is built on what's called a mixture of experts, or MOE system. The best way to think about this is like a massive 2.8 trillion book library. The model holds all of this specialized knowledge, which is broken down into 896 different experts in total. But to answer any specific question you throw at it, it only needs to pull a few of those books off the shelf.
Now, what's really interesting about this setup is the incredible disparity between what is stored and what is actively being used. Out of those 2.8 trillion parameters, which represent the model's resting capacity, only 16 of those experts actually fire at any given time. That means a mere 1.7%, or roughly 50 billion parameters, activate per token. Because of this, the actual computing power you need to generate an answer is surprisingly low. It behaves more like a mid-size model. But, and this is the whole crux of the 1.4 terabyte paradox we're talking about, you still have to build a library big enough to house all 2.8 trillion parameters in memory, just in case they're needed.
And wait, because the memory demands don't actually stop at the resting weights, Kimi K3 also boasts a massive 1 million token context window. Now, they do use a hybrid linear attention design called Kimi Delta Attention to try and make this somewhat affordable. But make no mistake, keeping the history of up to 1 million tokens active during a live conversation is going to push your live memory requirements even higher than that 1.4 terabyte baseline once the system is fully operating.
So, what does this actually look like in a physical data center? Honestly, it's brutal. If you're running current generation server hardware, you'd need a bare minimum of 18 separate 80-gigabyte GPU cards just to load the resting weights. And that leaves you with absolutely zero room for that 1 million token conversation history we just talked about. Even if you upgrade to an absolute maximum spec next-generation node, we're talking NVIDIA's Blackwell or AMD's MI400, utilizing 8 massive 192-gigabyte cards, you still barely fit the model. You are operating with almost zero memory headroom. This insane hardware floor fundamentally changes the entire business of artificial intelligence. Because of K3's MOE design, the actual active compute power is cheap. The new bottleneck is simply memory hosting.
The cost of running this frontier AI is no longer about how much math the chips can do. Instead, inference cost is now effectively measured in tokens per megawatt. It's about the pure electricity required just to keep 1.4 terabytes of static memory warm and resident on a server.
And this brilliantly illustrates a really harsh reality for the AI community right now. As the source material points out, at this scale, open source and accessible are no longer synonyms. Historically, the real magic of open source AI was decentralization, pulling weights down onto your own local workstation or a standard server rack. But a 1.4 terabyte baseline, that completely halts true edge deployment for models of this caliber.
But look, this doesn't mean K3 is useless for businesses. It just requires a totally new playbook. Some recent benchmarks by Fireworks AI revealed a really brilliant new strategy: routing. Instead of relying on just one model, you put an AI gateway in front. You let a smaller open model handle the bulk of the work, say 72 to 96% of your daily traffic. Then, you use a massive frontier model like K3 or maybe Claude Fable 5 solely as a fallback to catch the really tricky edge cases. In independent tests, this combined routing approach achieved 93% accuracy. It actually beat both models individually, and it did it at up to a 50x lower cost for long tasks.
So the crucial point we're getting at is this. For most enterprises, downloading and self-hosting Kimi K3 on your own 1.4 terabyte GPU cluster is just not going to happen. Instead, companies are going to rent K3 through APIs or managed cloud providers who can actually afford the Blackwell or MI400 silicon. In adopting these massive open weights, you're essentially trading a single vendor lock-in for a multi-vendor infrastructure dependency. You have more choices of who to rent from, sure, but you still have to rent.
Which brings us to the ultimate paradox of Kimi K3, and a thought I really want to leave you with at the end of this explainer. Moonshot AI has given the world this brilliant 2.8 trillion parameter gift, but if actually turning that gift on requires millions of dollars in highly specialized, power-hungry cloud infrastructure, who really owns the future of AI? Does releasing massive open weights truly democratize artificial intelligence, or does it simply re-centralize power right back into the hands of the giant infrastructure owners who can afford the memory? It is a fascinating shift in the landscape for sure, and one we'll be watching very closely. Thanks for joining me on this deep dive.